Hello, a great welcome to this presentation. In this video, we will provide you a sample calculation for the static vertical stiffness of a raft foundation. Please note that a detailed procedure for such a calculation is already provided in another video, the playlist for which is provided at the end of this presentation. So let us start with the example. So, okay, in step one, we have to define the raft geometry as well as the soil parameters. As you can see that here is shown a rectangular raft, and we will consider the length of the raft as 25 meters and its width is 15 meters. As you can see that here is the cross section of the raft wall assembly. The depth of embedment is 4 meters, and the engineer has considered a contact length of 3 meters between the side wall as well as the soil. And here is defined the soil parameters. The important one are the shear modulus, that is 75 MPa, and the Poisson's ratio is 0.33. And as you can see that this is the set of input parameters, and I think that here is one more additional parameter, that is the depth to bedrock. That means the bedrock is likely to be available at a depth of 60 meters from the ground surface, because this parameter is also likely to have a strong influence on the computation of the vertical stiffness. So let us go to step number 2. In step number 2, we'll proceed for the calculation of the static vertical stiffness, considering it as a surface foundation supported on an elastic horse base. So this is the situation that represents step 2, and please remember that this is how we should start. Okay, and in this case we shall proceed for the computation of the vertical stiffness using the standard formula K z surface is equal to 2 into GL divided by 1 minus nu into 0.73 plus 1.54 into B by L raised to 0.75. Remember, this formula has essentially two sets of parameters, one relevant to the geometry of the raft through the B by L as well as the L parameter, and the second set is the soil parameters, that's the shear modulus as well as the Poisson's ratio. So substituting the input values, we obtain the static vertical stiffness of the surface foundation as 49,80,970 kilonewton per meter. Please remember that this is the static vertical stiffness of the surface foundation that is supported over an elastic horse base. So we started with step 2. Now let us proceed to step 3. And in step 3, we will compute how the stiffness obtained in step 2 need to be adjusted for the presence of a bedrock at a finite depth. If you remember, we assumed that the bedrock is available at a depth h is equal to 60 meters below the surface, and we need to correct the stiffness obtained in step 2 through this presence of the bedrock, and this is being done through the parameter f1, which is defined as 1 plus b by h divided by 0.5 plus b by L. Remember, here h is the depth of the bedrock measured from the surface, and as clearly mentioned in the input, h is equal to 60 meters. So if we input all the parameters here, that is relevant to the raft geometry as well as the depth of the bedrock, we find out the factor f1 as 1.11. What does this mean? This means that the stiffness obtained in step 2 need to be increased by 11% in order to account for the effect of bedrock. So in step 3, we obtained the influence of the bedrock on the computed vertical stiffness. Now let us proceed for step 4. In step 4, we will calculate another factor f2 to account for the embedment depth of raft, that is a capital D. Remember, in step 2, we assumed that the raft is supported on the surface of the ground. But in the actual situation, we know that the raft is supported at an elevation D below the ground surface. And this embedment depth D will have an influence on the computed stiffness. And this influence will be taken through the parameter f2, which is computed as f2 is equal to 1 plus 1 by 21 into d by b into 1 plus 1.3 into b by l. Substituting all these values, we obtained f2 as 1.05. This means that the stiffness computed in step 2 need to be increased by another 5% in order to take care of the embedment depth of the raft. Now let us proceed to the next step, that is step 5. In step 5, we will introduce another factor f3 that account for the contact of the side walls with the soils. Remember, this parameter is again required because in step 2 we considered only a surface foundation. Now we need to introduce how the wall to the soil contact is going to change the computed static vertical stiffness, and this is done through the factor f3, which is computed as f3 is equal to 1 plus 0.2 into aw by ab raised to 2 by 3. Remember, here AB is nothing but it is a bearing area of the raft. Obviously, we know that it is nothing but the length into breadth because we have a rectangular raft foundation. Substituting the dimensions 25 into 15 will provide us 375 meters square. And here AW is nothing but the side wall soil contact area. That means the contact area all along the perimeter due to the contact length of a small d. Obviously, we know that is nothing but the perimeter into the contact depth d, that is 2 into Lx plus Bx into d, which will provide us 240 meters square. Now substituting the values of AW and AB, we obtain F3 is equal to 1.15. Remember, this is a very important factor. That means we observe that due to the contact between the wall and the soil for a specified depth of small d, which is equal to 3 meters in our problem, the stiffness will increase by a whopping 15%. So we considered the influence of all the parameters, whether it is the presence of the bedrock, whether it is the embedment of the raft, or whether it is because of the wall to soil contact, all into our stiffness calculations. Or in other words, we started with a classic case of surface foundation, modified the stiffness of this surface foundation for the bedrock, for the embedment depth of raft, and also for the sidewall soil contact. So it means that now we are in a position to compute the final stiffness, which is being done in step 6. That is, we proceed for the computation of the static vertical stiffness of the embedded raft, which is simply nothing but the stiffness of the embedded raft case at embed is nothing but it is F1 into F2 into F3 into case at surf, which means that the computed surface stiffness need to be increased by through the parameters F1, F2 and F3. And now introducing all these parameters, we find that the stiffness of the embedded raft is equal to 66.58893 kilonewton meter. So please remember that the detailed procedure is given in another video. So you need to first go through that video before scanning this sample calculation report, because it will help you a lot, and it is already provided over here. And remember that I have uploaded many videos in my personal YouTube, that is including the steel connections, machine foundations, the Bacchus, Plaxis software and all, and some of the playlists are already provided over here. So that's all for this video. Thanks a lot for listening.